is just a simpler representation of the system of linear equations. You have here a given linear system, ax plus by is equal to z sub 1, cx plus dy equal to z sub 2. In matrix equation, this is in the form ax plus b, where a is the coefficient matrix, your x is the column matrix for the variables, and b is the column matrix for the constants. In its augmented matrix form, it is just equal to the matrix shown. We are just combining the coefficient matrix and the column matrix for our constants. So, the elementary row operations are the operations that we will use in working on with the augmented matrix of our linear systems. There are basically three elementary row operations. The first one is to add a multiple of one row to another. This is multiplying a scalar quantity to one row and adding it to another row. Next is multiplying a row by a non-zero constant, or this is just equal to scalar multiplication of a row. Next, interchanging two rows. Take note that performing any of these operations on the augmented matrix of a system does not change its solution. So, we now have the row echelon form. Now, what is this? It is a matrix if it satisfies these conditions. The first one is the first non-zero number in each row reading from left to right is 1. So if you will observe this given matrix, the leading non-zero numbers in each row is 1. So for the first row, that is the leading number 1. This is 0. The non-zero leading number is 1. And same as with your third row. This is called your leading entries. Next property that it needs to satisfy for it to become in row echelon form is the leading entry in each row shifts to the right in the successive rows. So if you will observe, in the first row of our augmented matrix, the leading entry is in the first column. On the second row, the leading entry shifts to the right of our first leading entry in the first row, and it further shifts to the right in the third row. Third property that it needs to satisfy, all the rows consisting entirely of zeros are at the bottom of the matrix as shown in the second matrix here. Next, we have the reduced row echelon form. A matrix is in reduced row echelon form if it is in row echelon form and also satisfies the following condition. So we have discussed a while ago the three properties of a row echelon form. It will be called a reduced row echelon form, or RREF, if it satisfies this additional property. Every number above and below each leading entry is a 0. So if you observe this matrix, the leading entries are 1 in each of the rows. Above and below these leading entries is 0. So this is a 0. This is a leading entry for the second row. Above it is 0, below it is 0. For the last row, that is our leading entry, above it is 0. So this is in reduced row echelon form. Let's find the solution of the system of linear equation by transforming it into the reduced row echelon form. So the first step here is to align the variables. This would be 4x plus 8y minus 4z equal to positive 4. For the second equation, we don't have an expression for x. This is equal to 0x plus 8y plus 5z is equal to negative 2. Next, we have negative 2x plus y plus 12z equal to negative 17. So now we have aligned the variables. We will transform it into the augmented matrix. So that is just 4, positive 8, negative 4, positive 4, 0, positive 8, positive 5, negative 2, negative 2, positive 1, positive 12, and negative 17. So this is already your augmented matrix. Now let's name this your row 1, row 2, and row 3. Before we can transform this augmented matrix into the reduced row echelon form, we need to transform it first into its corresponding row echelon forms. So to do that, we will perform elementary row operations. Remember that for the row echelon form, we have leading entry, a value, number, and a number. This is 0, leading entry, number, 0, 0, and the leading entry and a number. So for the row echelon form, the leading entry shifts to the right on the succeeding rows. So let's continue. So for us to remove this number and transform it to 0, we will perform operations between row 1 and row 2. So let's just copy row 1. And for row 2, we will multiply it by positive 2. So positive 2 times row 3 rather. So this would be 4, 8, negative 4, and positive 4. 2 times negative 2 is negative 4. 2 times 1 is 2. 2 times 12 is positive 24. And 2 times negative 17 is just equal to negative 34. So let's add these two rows. 4 plus negative 4 is 0. 8 plus 2 is 10. Negative 4 plus 24 is positive 20. 4 plus negative 34 is negative 30. So let us multiply this further by 1 over 10. So this is 0. We have here 1. 20 times 1 over 10 is 2. And this is negative 3. Let us change your third row by this result. This is our new third row. This is 1, 2, and negative 3. Okay, so for us to eliminate one of the values here, either of these two rows, we will perform operations between row 2 and row 3. So to do that, let's copy row 2 and add negative 8 times row 3. This would be row 2 is 0, 8, positive 5, and negative 2. Negative 8 times 0 is 0. Negative 8 times positive 1 is negative 8. Negative 8 times 2 is negative 16. And negative 8 times negative 3 is positive 24. So adding these two rows, we will have 0 plus 0 is 0. 8 minus 8 or 8 plus negative 8 is 0. We have 5 minus 16 is equal to negative 11. And we have here negative 2 plus 24. That would be equal to positive 22. So to reduce this to 1, we will multiply this row by 1 over negative 11 or negative 1 over 11. This will be 0, 0. This would be negative 1 over 11 times negative 11, that is positive 1. And then we will have negative 1 over 11 times positive 22. This would be equal to negative 2. So we now already have your new row 2. This is 0, 0, 1, and negative 2. Why did I not change row 3? Because that is already a leading coefficient 1. If we will retain the original row 2, that is 8, we will still perform operations on it for it to have a leading operation of 1. So I just eliminated row 2 and changed it into this value. So we already have your new matrix. This is 4, 8, negative 4, and 4. Take note that changing the designation of our rows will not change the solution for our matrices. So we can interchange these two values. Your row 2 will become your row 3, and your row 3 will now become your row 2. So this is 0, 1, 2, negative 3, 0, 0, 1, and negative 2. So we have our new augmented matrix or row echelon form. We still need to transform the first row so that its leading entry would be 1. We will multiply it by positive 1/4. So this would be equal to 1, positive 2, negative 1, and 1. 0, 1, 2, negative 3, 0, 0, 1, and negative 2. So we now have our row echelon form because the leading entries are all 1 and the succeeding entries moves to the right of from the previous rows. So this is our row echelon form. We can already solve the solution or find the solution of the system of linear equation by using back substitution for the reduced echelon form. So to do that, let's convert this back into its matrix equation. This is x plus 2y minus z is equal to 1. 0 plus y plus 2z is equal to negative 3. This is 0 plus 0 plus z equal to negative 2. So we already have your z equal to negative 2. Let's perform back substitution to solve for y. Your y now is equal to negative 3. Transpose this to the other side. Minus 2 times z, which is negative 2. So this would be equal to y equal to negative 3. This is positive 4. So y is equal to positive 1. So for x, that would be equal to 1 minus 2 times y, which is 1, plus z. Your z here is negative 2. So x is equal to 1 minus 2 minus 2, or that is x equal to 1 minus 4, or that is negative 3. We have already solved your system of linear equations by just looking for the row echelon form of our matrix. But we can still convert the row echelon form into its reduced row echelon form for us to easily have the values of our variables x, y, and z. And let's try to do that. This is our row echelon form. By the way, the process of converting an augmented matrix into its row echelon form is what you call your Gaussian elimination. And the process of converting an augmented matrix into its reduced row echelon form is what you call your Gaussian Jordan elimination. And that is what we are going to do in the next parts. So for this matrix to be in reduced row echelon form, we need to change these numbers into 0 so that the values at the top and the bottom of our leading entries, these are the leading entries, would be equal to 0. So to do that, we will perform elementary row operations. So this is a row 1, row 2, and row 3. So for us to eliminate this number, let's perform an operation between row 1 and row 2. We will multiply row 1 by 2 and add it to row 2. This would be our solution. 2 times 1 is 2. You have here 4. 2 times negative 1 is negative 2. 2 times 1 is 2 rather. And let's just copy row 2. This is 0, 1. This is positive 2 and negative 3. Adding these two rows, we will have 2. This is 5, 0. And we have 2 minus 3 is equal to negative 1. So we have already transformed the first row into this. Is already our first row. Let's change this first row. This would now be 2, 5, 0, and negative 1. Okay, let's continue. We still need to eliminate this number. Let's change it to 0. To do that, we will perform operations again between row 1 and row 2. So let's just copy row 1 and add the negative 5 of row 2. It would be 2, 5, 0, and negative 1. So multiply negative 5 to row 2. That would be 0. Negative 5 times 1 is negative 5. Negative 5 times positive 2 is negative 10. And then we have negative 5 times negative 3 is positive 15. So adding this, we have 2. This is 0. Negative 10 and negative 1 plus 15. So this is 15 minus 1, that is 14. If you will notice, this is not 0. So one clue there is that you need to first change this value before changing this one. So you will not go back to your solution. So this is our new row 1. Let's change this into 0. This is negative 10 and this is positive 14. Okay, so we have our new matrix. For us to eliminate this number and to change it to 0, we will perform operations between row 1 and row 3. So let's copy row 1 and then we will add it by 10 times row 3. So row 1 is 2, 0, negative 10, and positive 14. 10 times 0 is 0. This is still 0. 10 times 10 is 10. And this would be 10 times negative 2, negative 20. Adding these two together, we have 2, 0, negative 10 plus 10 is 0. Sorry. And 14 minus 20 is negative 6. So this is our new row 1. We can still change this by multiplying it by a factor 1/2. So this would be 1, 0, 0, and negative 3. So we have now transformed our row 1 into 1, 0, 0, and negative 3. We have satisfied the condition for the reduced row echelon form for row 1. You only need to change this value into 0. And to do that, you will perform operations between row 2 and row 3. So let's copy row 2 and then add negative 2 times row 3. So row 2 rather, this is 0, 1, 2, and negative 3. This is 0, 0, negative 2 times 1 is negative 2. And then, negative 2 times negative 2 is positive 4. Adding this up, we have 0 plus 0 is 0, 1 plus 0 is 1, 2 plus negative 2 is 0, and negative 3 plus 4 is equal to positive 1. So this is our new row 2. If you will notice, we have already transformed our matrix into its reduced row echelon form because all the leading numbers have a number 0 above and below it. So this is already the reduced row echelon form.